Hello and welcome to lecture number 4. In this lecture and the next one, we will be covering Newton's laws of motion. And Newton's laws of motion are mainly concerned with forces. What is a force? A force is an action that changes the state of motion of an object. So before I talk about Newton's laws, I want to define the meaning of the word force according to Newtonian physics. So what is the force? The force is an action that changes the state of motion of an object. What does that mean? Well, suppose that you have something sitting on the table, okay? Say a book or a box or whatever. And the box is sitting there. It is at rest. Nothing is happening to it. Now, when I apply a force on the book, say, for example, I would give it a push in this direction. Here is my vector, the force vector. And I would give it a push in this direction. What's going to happen? The box is going to slide on the table. Let's say it's going to slide and until it stops or something. So what happened was I have changed the state of motion of the object. Initially, the box was at rest, and then by applying the force, I put the box into motion, and I moved it to a different place. So now it is, say, situated here. Okay? So that's basically what the meaning of the word force. So it's an action, okay, that changes the state of motion. So the state of motion here, for the situation that we're dealing with here, so the state of motion of the box was at rest, and then we changed it into a state of motion where it moves from this location to, say, this location. You see what I'm saying? Another example, say for example, you're driving your car and let's say you're going, say, 25 miles an hour and constant speed, for example, and then you decide you want to stop, so you push on the brake. The brake is a force. So what will happen, you have slowed down the car. Now the car is moving at a lower speed. So the force, which is the braking force, okay, that's kind of a friction force. Again, it's an action that changes the state of motion of your car from the state of motion of 25 to something else, okay? The same thing is happening if you push on the accelerator. Here you have a force on the engine that would force the wheels to rotate it or spin faster, and then you would go faster and so on. So that's the meaning of the word force. Newton's first law, so there are 3 laws for Newton. Newton's first law I'm just going to go like this, basically says objects at rest remain in the state of rest, and objects in motion remain in the state of motion unless they are acted upon by a force to change their state of motion. Okay? So objects at rest remain in the state of rest, and objects in motion remain in motion in a straight line unless they are acted upon, or compelled, acted upon by a force to change the state of motion. Okay? That's Newton's first law. It's called the law of inertia. So again, I want to read it while we're looking at the box here, the example of the box here. So we have an object at rest, remain in the state of rest. And then if you have an object that is in motion, now if it's in motion and there are no forces on it, okay, that object is not going to stop, because in order for it to stop, there has to be a force to stop it. You see what I'm saying? So if it's in motion, it will stay in motion, but in a straight line. Okay, we'll learn later about this details, that if it's not moving in a straight line, then there is a force on it. Okay, so if you have, what I'm trying to say here, or what Newton is saying here, is that if you have an object where this object has no forces on it, there are two possibilities for this object. Either it will be at rest, okay, which means that there are no forces on it, or maybe all the forces on the object cancel out. That's one possibility. The second possibility is that the object will be moving in a straight line at a constant speed, okay? So in other words, if there are no forces on an object, it can be moving in a straight line at a constant speed, simply because there is no reason for it to stop. Again, in order for it to stop or to change its motion, there has to be a force on it. And there we go. Unless they are compelled or acted upon by a force to change their state of motion. So what changes the state of motion of an object? The force. And what is the force? It's an action. Go back to this one. It's an action that changes the state of motion of the object. Okay? That's basically Newton's first law. Newton's third law, I'll come back to the second in a minute. Newton's third law says that for every action, there is a reaction. For every action, there is a reaction equals in magnitude and opposite in direction. Okay? For every action. What is action now? You remember what action is? Go back to the very first line right here. The force is an action. So for every force, action is the meaning of the word action. In Newtonian physics, it means force. So for every force, for every action, there is a reaction that is equal in magnitude. Here we're talking about vectors, you know, the magnitude of the vector, and opposite in direction, okay? More on this law as we start doing problems. But basically, let me explain it to you in a simple way. Let's say you make a fist with your hand and you punch the concrete wall, okay? You will know, as you know, that the harder you hit the wall, the more pain you feel in your knuckles. Now, why is that? Because you're exerting an action on the wall, and the wall exerts a reaction in the opposite direction on your knuckles, and therefore you feel that pain. And the amount of force that you are exerting on the wall is equal to the amount of force that the wall exerts on you. You see what I'm saying? That'd be a simple example, but as we go along, I will show you how this law applies to other situations. And then the last law is Newton's second law, which is the mathematical law. And it basically says that the sum of the forces on an object, it gives it what we call a kinetic reaction, MA. So if I have forces on an object, several forces on the object, okay, the sum of the forces, as a result of these forces, what will happen is that the object is going to move in an accelerated motion, and what we call the kinetic reaction. Okay, that's basically what the second law. Again, I like to teach you those laws through working out examples so you can actually see what's going on. So that's basically the laws of Newton. So let me begin with simple examples. But before I move along, let me just go back to the second law here. So if you have, let's say, for example, let me go back to that box problem right here, this one here. And so I have here a box or a book sitting on the table. So here is the surface of the table or the floor or whatever. And suppose I have a box here. Okay. And it's just resting there, minding its own business. Now we ask the question, what are the forces on the object as it sits there? Well, it has its weight. Okay, so that is the weight of the object, right? It's pressing on the floor, just like you are sitting on the chair right now, and you are, with your weight, you're pressing on the chair, right? The seat of the chair, if you will. So here is the weight here. I'm going to call it W. Okay. Now, is that it? Is there more other forces there? Well, we need to appeal to Newton's third law. Look at the third law. So what the third law says: for every action, for every force, there is a reaction. In other words, all forces come in pair. Well, the action here is the weight. So you have the book sitting on the table, resting on the table, and it's giving an action, which is the weight of the book. So this means that there must be a reaction opposite in this direction that is equal in magnitude and opposite in direction. We call that the normal force. More on it later. Okay, that's called the normal force. Okay, so this normal force is equal to the weight of the book. And let's go to the Newton's second law. He said the sum of the forces. So if I'm going to take the sum, which means I'm going to add the normal plus the weight, what do I get? Well, it is the normal is positive because it's moving up or directed upward, minus W. What is that equal to? Well, they are equal to each other, aren't they? According to Newton's third law, which is for every action that is a reaction equals in magnitude. We are talking about magnitude here. And opposite in direction. There we go. They are opposite. The normal is positive. The weight is negative, as you can see in the picture here. And that will give us really zero because they're equal. Okay? In other words, it doesn't give us a kinetic reaction. It doesn't give us motion. Okay? And that's okay. You got it? So this, when you have the formula, the second law of Newton, when sigma F equals 0, we call this state, we call it state of equilibrium. As a matter of fact, anything you see at rest or moving with constant speed, in other words, it's not accelerating, not speeding up, or it's not slowing down, it's basically the sum of the forces on that object is equal to 0, and therefore it's in the state of equilibrium. Okay? An example of a state of equilibrium would be, well, the example that I'm about to do right now. So let me go to the book. We are in chapter 6. And the example is this one. Look at this one. So what you have in here, you have those, let's read the problem first. Read it, we'll read it, and then you look at the diagram here. It says the 3 ropes in the figure, there they are, rope number 1, 2, and 3 here, sorry, 1, 2, and 3, are tied to a small, very light ring. The ring is right there, this one right here, okay? 2 of these ropes are anchored to walls at right angles with tension shown in the figure. All right, so we have a tension here. We have tension T2, tension T1, so we have 80 Newton. By the way, Newton is the unit of force, okay? Please read from the book before you watch the video because I can't tell you all the details here. The purpose of those videos is to work out problems, as many as possible. You know, you want to read from the book and then you come here to solve problems with me. Anyway, so we have here, the tension is 80 Newton, this one. The tension here, T1, is 50 Newton. And then we have, let's read the problem. So what does it say here? Two of these ropes are anchored to the wall at right angle with tension shown in the figure. What are the magnitude and direction of the tension T3 in the third rope? Okay. In other words, these are in equilibrium. In other words, all these forces together combined will cause the whole system, the whole dynamical system, to be in equilibrium. Okay. This magic word that you need to know, the word equilibrium. Okay. Again, what is equilibrium? Equilibrium means the sum of the forces on an object gives you zero. Okay? You need to know that very, very, very well. Okay. So let's work out this problem. So what I have in here, so here's one wall. Here's the other. And then I have I have one rope like that, and then one rope like that, and then we have a tension, or somebody's pulling on it like that. I'm going to call that T3. Okay, and then we have here the length of this rope. This is 0.8 meters, and this one is 0.6 meters. Okay, and this is tension 1 equals 50 Newton, and this is tension 2 equals 80 Newton. Let me show it to you again. I'm copying all of that from my book that I have beside me right here, and right there. Okay, so there it is. All right. Got it? So you want to know what T3 is. Okay, so how do we do this problem? Simple. The first thing you need to do is you want to draw the free body diagram. What that means is that, see this knot right here, the ring that he's talking about? I'm going to draw it right here. Watch. Here it is. Here it is. Okay, and I'm going to put all the forces. So I have tension 2. Which direction? What is the direction of tension 2? Okay, keep something in mind, all right? This is very important. Tension always come out of the body, all right? So the body here is basically the ring. So tension 2, if you're wondering, is it going this way, the tension 2, or is it this way? It's always out of the body, okay? So out of the body, that means it's out this way. So this is tension 2. And then we have tension 1, again, out of the body, always out of the body, and that's tension 1, okay? And then we have tension 3 going back like this, again, out of the body. It's already there anyway, okay? And we want to know the net, we want to know what T3 is. Well, how do we do it? Okay, so I need, because T2 and T1 are, the T2 is vertical, T1 is horizontal. There's no problem with that. But T3 is an issue here because it is not vertical, it's not horizontal. It has two components. Let me change the color and just work it out for you. So T3 looks something like that. So we have here, I have T3 going this way. T3, if I have an angle here, which is not given to me, I'm going to call it theta. This angle is T3 cosine theta. And then I have here T3 with a minus there, okay? But I'll talk about the minus later. Will be sine theta. But I don't have theta. So how do I find it? Okay. So the reason he gives me those lengths here is to help me find the angle theta. So the next step now, I want to put this, I want to appeal to Newton's second law. So we have here the sum of the forces in the x direction equals 0. And then I have the sum of the forces in the y direction equals 0. Now, why are they equal 0? Because the system is in equilibrium. It's not moving, right? So everything is in equilibrium. So now, what are the forces in the x direction? Well, I have T1 minus T1, and I have T3 cosine theta. Remember, I don't know what theta is yet, okay? So here I have minus T1 plus T3 cosine theta, and that's equal 0 in equilibrium, all right? Now we come to the y component, so we have two of them, T2 minus T3 sine theta. So I have here T2 minus T3 sine theta equals 0 because, again, it's in equilibrium. Remember, he's asking me to find T3, but I'm discovering that I don't know the angle theta. You see what I'm saying? So first I need to find theta. The good news, he gives me T1 and T2, here they are. So let me just put them down there or up here. So that will be 80 Newton, and T1 is equal to 50 Newton. I can put them in there if I want to, but I like I said in the previous lectures, I like to solve the symbolic formula first. So what I could do now, if I would, let's say, take the x component and solve for T3, look what will happen. So I have here T3 cosine theta equals T1. So T3 is equal to T1 over cosine theta. Is that okay so far? I have that. Let me box it. I'll come back to it in a sec. There are different ways of doing it. This is just my way. I'm going to do the same thing when we solve for T3. So I have T3 sine theta is equal to T2. So therefore, T3 equals to T2 over sine theta. Okay? So I have those two equations. Logically, they're equal to each other, right? Because they are T3, T3. So I can equate them together. Equate. So in this case, I'm going to have T1 over cosine theta equals T2 over sine theta. And I would like to get something, a ratio of sine theta over cosine theta, because I know it's equal to tan theta. I hope you see what I'm doing here. I want to get that ratio. So what I can do, I can cross multiply, and I'm going to get this. Sine theta over cosine theta, that's equal to T2 over T1, or tan theta equals T2 over T1. The good news is I already know what T2 and T1 are. Here they are, 80 and 50. I can plug them in there. So therefore, tan theta equals 80 over 50. Take the zeros out. So therefore, theta is equal to tan inverse of 8 over 5. You see that? And I can use my calculator. I hope you're working with me as well. Make sure your calculator is in degrees. So I have inverse tan 8 divided by 5 equals, I got 58 degrees. So in this case, theta is 58 degrees. I'm going to box it. Okay, I'm almost done with the problem. Now I can pick one of the expression for T3. Remember, he's asking for T3. I get this one or this one. It doesn't really matter to solve for them. So I'm going to pick this one right here. So I have, oops, sorry. So I have here, I'm going to take that. And this will give me T3 equals T1 over, I forgot how it looks like. What is that? Cosine. All right, so cosine theta. And then you just plug it in. Sorry for my goofy handwriting. Theta, and this is 3. So I have here T3, T1 is, what is it? 50 divided by cosine 58, and therefore finally, so T3 is equal to, let me do that. So I have 50 divided by cosine 58. Answer, I got 94.4. So I have 94.4 Newton. And there we go. I have the value of T3. This is actually a little bit a harder problem. I should have maybe started with something easier, but I hope you followed me. Got it? Okay. All right, let's do one more. Here's one for my notes. Actually, is very similar to the one we are doing right now, well, the one we have just done. Okay, here's one from my notes. It's an inclined plane problem. So what I have in here, make sure you understand the inclined plane. The inclined plane problem. Okay, so what you have in here, imagine you have a ramp. Here's a ramp. Okay, and there is a car that is being towed up the ramp like this. Here is the car. Okay, there it is, and it's being towed. Okay, so there is some crank somewhere here, and it's pulling it with some tension T. Okay, now the weight of the car W is 15,000 Newton. Okay, now what is the weight? Let me just back up here a little bit. Weight, it's basically W is equal to the mass times G, G being 9.8. For example, if my mass is 85 kilogram, okay, let's say that this is my mass, then my weight would be 85 times 9.8, and when I do that, that's equal to 833 Newton. Okay, that's basically what weight is. Got it? So when we talk about weight, the word weight, immediately the unit here is Newton, not in kilogram. All right. So anyway, so this is the weight of the car. If you want to know what the car is in kilogram, well, divided by 9.8 is this number. So anyway, here it is. Okay, and then this ramp or this inclined plane is inclined at an angle of 20 degrees. Okay, and he's asking for how much tension to pull it with without accelerating the car. So what is the tension? Here's the question. What is T, the tension T, without accelerating the car? In other words, A is equal to 0. In other words, I want to pull it up the ramp with constant speed. Okay, so it's constant speed. Constant speed. That's the meaning of it. Now, what does that mean when we say constant speed? It means that the forces on the car, remember sigma F equals ma, well, this A is 0. This A right here is 0. So that means it's 0. There is really no acceleration. So basically equilibrium again. Okay, we're going to deal with some problem with MA later. For now, I'm trying to be, I want to show you how to work out problems where sigma F here, sigma F right here is equal to 0 for now. Okay, so anyway, that's basically what the problem is, and we want to solve this problem. So we want to know, what is the tension? Okay, so to work it out, so I hope you've taken notes on that. So here is the car. Here is the ramp again. I'm going to turn the car into a block because I'm going to draw it as a free body diagram. I don't need to draw a car. And I'm going to ask the question, what are the forces on the car? Okay. Well, the first force is the weight. What's the direction of the weight? It's always toward the center of the earth. And so that means it's going down this way. That's the weight of the car. Remember we talked about the weight. The weight is equal to what? The weight is equal to W equal 15,000. And W is mg. I like to just call it mg explicitly, like that. Okay? So I'm going to call it mg. You can call it W if you want to, but I prefer mg. So mg means weight. Okay, according to Newton's third law, for every action there is a reaction, remember? And so there is a normal force, and the normal force is always perpendicular to the surface. Okay, so this the normal force in this case is going to be like this. That's the normal force. And the object, the car, is being pulled with a tension T. There it is. It's parallel to the incline, T. And we are asking, what is T that will cause the car to move at constant speed or non-accelerating motion? Got it? Okay. Now, how do I do that? Well, again, I need to put in my X and Y coordinate. Now, I can put my X and Y coordinates like this, but this one is not, it's not wrong, but it's just not convenient. When you deal with an inclined plane problem, the best datum or reference X and Y coordinate is you put them like that. You know, let me put them here. Like this. X and Y. See what I'm saying? Let me change the color. So in this case, the tension is along the x-axis and the normal is along the y-axis. See how convenient it is? The only one that is out of line is really the weight. Okay? So see, the weight is this way, which is basically, if you're going to draw it here, it's going to look something like that. Here's the weight. Okay? Whoop! Ah, gosh. Got it? Okay, so here's my X and Y right here. Okay, so what I want to do, so I have here this angle right here. This angle right here is actually equal to this angle. You can pause the video and try to convince yourself of that. It's basically basic geometry. Anyway, so what I want to do now is I want to resolve mg into x and y components, because n is already in the y direction, t is in the x direction, as you can see from the datum that I have created here. The only one that is crooked, if you will, or oblique is mg. So I'm going to have here mg to be equal to this, mg, cosine theta, going to be this way. That's mg cosine theta. And then I have mg sine theta going this way. Okay, then once I get those components for mg, I can simply ignore this mg because it has been replaced with its own components. Okay, I hope you understand that. We covered that in the previous lecture, lecture 3, where we covered vectors. Okay, and that's it. We are ready to solve this problem. So now remember, the car is moving up the ramp with constant speed, which means the acceleration is 0. So now when I put in my Newton's second law, sigma f equal ma, it's not really ma, it's 0. So I have here too, I have sum of the forces in the x direction equals 0, and sum of the forces in the y direction equals 0. So what are the forces in the x direction? Well, as you can see from the diagram, I have t minus mg sine theta, and on the y-axis, I have n minus mg cosine theta. So here I have, and remember, this direction is positive and up is positive. So I have here t minus mg sine theta equals 0. And then on the y-axis, I have n minus mg cosine theta equals 0. I got that. Okay? Again, we ignore the mg here. It has been replaced again by its component. Got it? Okay. Remember, the whole purpose of this problem is to solve for t. I need to find a way to solve for t. Now, do I have everything? Well, I have the weight mg is given to me, the angle is given to me, and I am pretty much done with the problem because I have I'm supposed to solve for t. So t is equal to mg sine theta, and I have everything. Mg is equal to, go back to that, there we go, it's 15,000. So I have here sine 20, and there we go. So I can use my calculator for that. So I have 15,000 times sine 20. Answer 5,130.3 Newton. There we go. That's how much tension the tow truck needs to pull the car in order to have it move with constant speed. Now let's, for the sake of completing the problem, what is the normal? Well, the normal, go back this equation right here. So the normal here is going to be normal is equal to mg cosine theta, and I have everything again, 15,000 times cosine 20. So I have here 15,000 times cosine 20. I'm using my calculator. 14,095, if I did it correctly, 14,095 Newton. And there we go. This is the normal vector that I have. Okay? Okay, good. One more problem. I want to do another important problem in physics, and that is the Atwood machine. The Atwood machine. So what is the Atwood machine? It's one of the simplest pulley systems out there. This is one of the most ancient pulley system that has been used by many ancient people, different civilization all through history to lift things up. Okay? For example, let's say, the pyramid. How did they manage to lift those big bricks to the top of the pyramid, for example? Or let's say you want to lift some big statue. You have it on the ground and you want to lift it on top of a mountain, on top of a cliff. How would you lift something like that there? It would be difficult to have just manpower, to have a bunch of guys, lifting it, especially if it's really big. But the Atwood machine can manage to do that. And the way it works is this. Imagine you have a pulley. Here's a pulley. Okay? And you anchor the pulley, or you hang it from here. And then you have two weights. One weight here and another one. One weight and a counterweight. Like that. Mass 1, mass 2. Now, if they are equal in mass, a little child could actually, if they are equal in mass, let me put them in, sorry. If they are, if they are, hold on, I'll shut up until I finish drawing it. I can't get a straight line out of this thing. Okay, so let's say I have two of them like that, and suppose that the two masses are equal. Okay, so what's going to happen? They're going to be level like that. Nothing, no one will, neither two nor one will move up or down. Right now, if you bring a little child, that little child could actually press on, say, two and bring it down, and then bring one up. Even though, if you even suppose that two and one has a mass of 1 ton each. Okay, why is that? Because they are in equilibrium. Do you see what I'm saying? Do you see what I'm going with that? So that's the idea behind it, is that if they are equal in mass, the slightest force on, say, 2 will cause it to go down, and then this goes up. So now, if I want to lift a big statue to the top of a cliff, for example, here is the cliff. Okay, here is the top of the cliff. And here is the big statue. Okay, if I have, imagine if I have a pulley system here, somehow. So all I need, here is the weight of, here is the rope that is attached to the statue, and here is a counterweight. Okay, here's a counterweight. So all you need is you push on this down, this will go up, and I can put it up here. You see what I'm saying? That's the idea of the Atwood machine. It's like I said, it's an ancient machine, ancient way of lifting things, or it's used in construction and so on. All right, so that's what it is. So I want to solve the Atwood machine and get an expression, say, for acceleration. Okay. I'm not sure if I have it here. I can do it from my head. I don't need to look up anything. I don't think it's covered in the book. I'm not sure, but anyway. So let's do it. I don't have it in front of me. Okay. So suppose I have the pulley like that. Whoops. So here is the pulley. Okay, and I have one weight and a counterweight. Here is one weight. I'm going to call it 1, and a counterweight. Here it is, 2. Okay, and suppose M1 and M2 are not equal. Okay, so you have masses M1 and mass M2. We can put numbers to them, but it's not important. What I'm interested in is suppose that let's see. Suppose that M1 is greater than M2, okay? A little slightly greater. So what's going to happen? M2 is going to move up and M1 is going to come down, right? They're going to go, so until it hits the floor. Suppose that the floor is here, okay? So M1 is going to come down and M2 is going to go up. And as it's coming down, it's actually accelerating until it hits the floor, and M2 is going to go up, okay? So they both have, they will be accelerating here, okay? Here is something interesting about the pulley system, this what we call the Atwood machine, is that because we are dealing with only one cable, okay, this cable is right here, it goes around the pulley like that, and it goes to the other mass, okay, only one cable. What that means is the following, is that the speed of M1 going down is equal to the speed of M2 going up. So we have the same speed. So V1 is equal to V2. I'm going to prove it to you in a second. Also, the acceleration of M1 or block 1 is equal to the acceleration of block 2. Except what they are opposite in sign. So V1 is going down and A1 is going down. You know what I mean? So one going down if you look at it in terms of vectors. Okay, so that's basically what it is. Also, the tension in the rope here, whether it's the one attached to 1 or 2, is the same. So basically T1, the tension, is equal to T2. Okay, let me prove it to you before I do the equation of motion and F equals ma and so on. Imagine that this cable has a length, the cable that goes from here all around the pulley to one is, we're going to call it the length L. Okay, this L. Also, suppose that this part of the cable on 2, I'm going to call it Y2. The cable, I'm talking only about the cable. and then the part on in 1 is y1. Okay, and then you have the rest of it is this part, right? I'm going to call that S. So the length of the cable, the total length of the cable is basically y1 plus y2 plus S. S is basically the one that is, is on the circumference of the pulley. Got it so far? Okay. Now, let me take the derivative of both sides. Why am I doing that? I'll show you in a second why. So, take the derivative, the time derivative of both sides. Now, we are assuming that the cable is rigid, which means it's not elastic, and therefore the length here is constant. Okay? Also, what's constant? Well, the length S here is constant. Do you agree with me on that? No matter where M1 and M2 are, I mean, M1 could be way down on the floor and M2 way up, or vice versa. The S value of the cable is constant as well. So when I take the derivative, the time derivative here, this will be 0 equals to dy1 dt plus dy2 dt plus 0 for S. Okay, now I can move one of them to the other side. Say I want to move dy1 dt to the other side. So that gives me dy1 dt with a minus is equal to dy2 dt. Well, what is dy1 dt? Well, it's nothing but the velocity. So basically what this is minus v1 is equal to v2, and I have just proved this one. You see that? Okay, now if I continue on, so there we go, I have just proved it. Now if I continue on with this, if I take the second derivative, it's going to be minus d squared y1 dt squared equals d squared y2 dt squared. And what is that? Well, that's the acceleration. Minus a1 equals a2, which is this one right here. Okay? So there we go. I have just proved to you that the velocities of the two blocks in the Atwood machine are equal and opposite in direction. One going up, one going down. Okay? And the acceleration is also equal in magnitude, opposite in direction as well. Okay? In addition to that, the tension are equal. Okay? I'm not going to prove the tension for you, but the tension are also equal. Okay, that's something that I hope you'll keep that in mind. All right, so let me go back to the Atwood machine now and want to show you how we find the equation of motion. What I mean by the equation of motion, that means when we apply sigma F equals ma, and whatever equation we get, we call it the EOM. Excuse me, the EOM, the equation of motion. All right, so again, I'm going to draw it for the third time. And then we're going to get the equation of motion for the Atwood machine. So I have, here's the pulley, here's the pivot, here's 1, and here's 2. Again, you want to run a film in your head, see the motion. This one is going up, this one is going down. Excuse me. So what I'm going to do now, I'm going to take the system apart. I'm going to take block number 2 and put it right here. And block number 1 and put it right here. And then I'm going to put all the forcing on them. And remember, we said that you have the mass of block 1 is m1, and the mass of block 2 is m2, and the m1 is greater than m1. This is our assumption, all right? So, and then also, so here's block 2 is going up this way. So here we have a tension on 2. Remember, we talked about tension. It's always out of the body, never ever inside the body. Okay, keep that in mind. That's why I put the arrow here up. Why did I put it up? Because it's out of the body. Okay, keep that in mind. And then I have here the weight of the block, which is m2g. Same thing here. I have T and then m1g. I didn't need to write T2 and T1 because T's are equal. Get that? T1 equals T2 is, I'm just going to call it T. Get that? All right, now get the equation. So for block number 1, sum of the forces equal to M1A, right? I can call it A1, but A1 and A are the same, right? But the difference is that, remember, block 1 is going down. So that means if it's going down, let me erase this for a second. It's going to be minus because it's going down. The minus here means the block is going down. Got it? And F here, well, what are the forces? Well, yeah, they are T minus M1G. So that's going to be T minus M1G equals minus M1A. I have the equation of motion of block 1. Okay, I'll come back to it in a sec. Let me do block 2. This is block 1. Block number 2, I have T, sum of the forces equal plus M2A, plus because moving up, remember? So it's moving up, here's the arrow, moving up. So we have here T minus M2G equals M2A. I have that, okay? Suppose that I want to find, I forgot what the question is asking. Let's say that the question says, find the acceleration. Find an expression for the acceleration of the Atwood machine. Okay, that's basically the question. All right, so all I need to do now is I have two equations and I need to combine them together. So to combine it together, I can maybe, what's equal, the acceleration are equal here. The tension are also equal. Remember we talked VA and T. So I can solve for T. In other words, I can start with block number 1. I'm going to call this equation 1 and this is equation 2. So block number 1, I have here T equals to minus M1A plus M1G. Is that okay? And I'm going to take this and plug it into 2. Plug into 2. Because I want to eliminate the T and collect the A's. So now when I go there, so for 2, so I have here, start with T right here, which is this one. So substitute, so I'm going to have minus M1A plus M1G minus M2G equals M2A. Again, I'm solving for what? For A. So I'm going to take this one right here and move it to the other side right there, okay? And this, so I'm going to have here M1 minus M2, quantity G equals to M2A plus M1A. Take take A as a common factor. So I have M1 plus M2, and then finally, therefore, A is equal to M1 minus M2 over M1 plus M2G. And that's a famous relation that describes the acceleration of the Atwood machine. There we go. You got it? Okay. We'll do some problems later with numbers for the Atwood machine, but please do me a favor, do yourself a favor, go back to the beginning of it right here, and then try to solve this problem, break apart the blocks, and then get the equation of motion, and then arrive at this formula without actually looking at it. We're going to be doing a lot of Atwood machines problem like that. For those of you who are civil engineering or mechanical engineering, you're going to be taking two courses called statics and dynamics, and those two courses you're going to be doing a lot of basically the subject of this chapter, or the subject of this lecture and the next one. A lot of Newtonian physics, Newton's F equals ma. So I urge you to understand this material very, very, very well. You will see a much more complicated system than that. Okay, I have taken those courses, by the way. before I switched to physics when I was your age. I was in engineering and I took those courses. And I remember we have dealt with a lot of problems, more complicated than the one we're doing here. But I'm teaching you the basics. You need to know the basics before you get into more complicated problems. Okay? Okay, good. One more. This one is kind of an interesting problem. It's an example. Example 6.4. Let me pause the video. Okay, here is the rocket problem. This is an example in the book. Kind of an interesting example. It says example 6.4, altitude of a rocket. It says a 500-gram model rocket with a weight of 4.9 Newton is launched straight up. The small rocket motor burns for 5 seconds and has a steady thrust of 20 Newton. Basically, the thrust, that means it is a force that is pushing the rocket upward, right? What maximum altitude does the rocket reach? All right, and I think there is a picture of it. We don't have a picture. This is just part of the solution. Anyway, so let's draw a let's draw a picture of this thing. So what we have here is so you have a rocket that looks something like that. Here it is. And while the rocket is going up, okay, so what are the forces on it? Well, the rocket is accelerating with an acceleration A. The thrust force is moving it upward of 20 Newton. And of course, we have the weight of the rocket, mg, like this, all right? Now, let me give you a better picture. Okay, I'll come back to this diagram in a minute. But suppose that here is the floor, all right? And here is the rocket before we, turn the motor on. So here is the rocket, and it's just sitting there. Then we turn the motor on, and now the rocket is on its way up. So if I'm going to draw this picture, I'm going to draw it right here. There it is. And so we have the thrust of 20 Newton, and then we have the weight of the rocket, mg, okay? But if I go back to the problem, it says a 500-gram rocket weighs this much, is launched straight up. The small rocket motor burns for 5 seconds, okay? This is important. What does that mean? It means it's going to keep burning, okay, starting from here, okay? There is a thrust of 20. It's going to go up, and it's going to keep going up. And after 5 seconds, what's going to happen to the rocket? It's not going to stop and fall. It will continue to go, but after, it will continue to go as a free fall. So this is at t equals 5 seconds right here. And what will happen, the rocket will continue to go without the motor though, right? In free fall. So now the rocket is going to go up until eventually it's going to stop here. This is the maximum altitude reached by the rocket right there. Okay? So here we have two heights. The first height is that while the thrust is going for 5 seconds, this height, I'm going to call it y1. And then, whoops, like that. I think I pushed the eraser on the pen by mistake. And then here in free fall, I'm going to call it y2. So here we have to solve two problems here. Okay, so let's begin with while the thrust is going right here. So here we have sum of the forces equals to ma. M here is the mass of the rocket. And the forces here, what are the forces on it? There we go. Let's look at this picture right here. So that's going to be 20 minus mg equals ma. And what I want to do, I want to solve for the acceleration. So the acceleration is going to be 20 minus mg over m. And I have everything. He says that, go back to the problem, it says the mass of the rocket is half a kilogram right there, right? And with the weight, I mean, either or, right? Okay, and the weight of the rocket is 4 points. That's the mg of the rocket, that is, right? And then, okay. So we have here, the acceleration is 20 minus 4.9. He said the weight is 4.9, and the mass is 500 gram, which makes it 0.5, right? And then from there, I can find the acceleration. And when I calculate that, I'm going to get 30.2 meters per second squared. Now, what do I want the acceleration for? Well, I want the acceleration because I want to use kinematics to find y1. You see, I have acceleration now. The initial velocity of the rocket is 0, and with this acceleration, I can find the final velocity of the rocket, okay? So let me do that. So I can use kinematics here. Oh, and I know the time. So the time is given to me for 5 seconds, right? So now I know I can use the first kinematic equation. V equals V naught plus AT. V naught is 0. The initial velocity of the rocket is 0. So what is the velocity of the rocket right when the motor stopped working after 5 seconds? In other words, what is the velocity of the rocket right here? Why do I want it? I'll tell you in a minute. If you still don't see why you want it, I'll tell you in a minute with that. So anyway, I can find that thing by using kinematics. So this one, so I have V is equal to, well, I'm here, right here. So equal to A, I just found it to be 30.2 times the time is 5. So the velocity of the rocket by the time the motor stopped is 151 meters per second. Okay? I'm going to box it. Okay, now if I know that, I want to find the height, this height right here, y1. How do I find it? I mean, I have pretty much everything. I know the initial velocity is 0. I know the final velocity is 151. I know the time. I know everything. So it becomes a simple problem to find y1. I can use really any equation I want to. Let me use the middle one, which is this one. V squared equals V naught squared plus 2ay, y1 that is. And then the initial velocity is 0. And I'm solving for y1, so that's going to be v squared over 2a. And I have everything. So in this case, I'm ignoring the minus sign, right? Because there is a minus sign on the y. So anyway, so here we have v squared is going to be 151 divided by 2 times a is, what is it? 30.2, it's right there. And then I can calculate y1. When I do that, I will get 1,163.3 meters. So I have now calculated hold on, I'm sorry, maybe I'm not let me calculate one more time. I want to make sure I'm doing it right. Divided by 30.2 divided by 2. Sorry, I got this is the wrong answer. I just didn't look right. Okay, the right answer is 377.5 meters. And there we go. Okay, I have gotten the initial height right here. You see what I'm saying? Now I want to come here. What's going on here? Well, think about it. The motor of the rocket stops, so that means the rocket is still moving at very high velocity, 151, the one we calculated right here. Okay, so it's going to keep going up as in free fall, where the acceleration of the rocket here is what? Is g. 9.8. And eventually the final velocity of the rocket here is going to stop. So that means this is 0. Okay? So we have y2 here. So you can think of this v as the initial velocity of the rocket in free fall. The final is 0. And now with those two in mind, and I know that a is equal to g here, the acceleration is in free fall, I can easily find y2. Which equation do I use? I can use the same equation, this one, but as a free fall equation. So now we have a free fall stage. Which basically motor stops. Right? So in this case, I can use the same equation. V squared equals V naught squared minus 2GY2. The final velocity here is 0. I hope you believe that, right? Because eventually it stops. The initial velocity here, guys, is basically this one for the free fall, right? And that's it. I can solve for y2. So in this case, I can solve that y2 in this case is going to be equal to V naught squared over 2g, and that will give me 151 squared divided by 2 times 9.8. And then I'm going to calculate that, and that will give me 151 squared divided by 9.8 divided by 2. Answer, it's the same number that I got as a mistake, but anyway, here it is. 1163.3 meters. Okay? So let's go back, and the drawing here doesn't give it justice, because it looks like here in the drawing y1 it looks like it is larger than y2, which is not true. This one is only 377, where y2 is much greater, 1,100. But anyway, so what's going on here? Let's go back. Let me recap, and I want to make sure everybody understands this. So the rocket is launched, initial velocity 0. The motor is working. The motor is pushing the rocket with 20 Newton to move it up. It goes on for 5 seconds. After 5 seconds, motor stops, right? The rest of the trip is free fall trip. Okay, so here we have 2 stages. Stage number 1 and stage number 2. Stage number 1 is the motor is working and with a specific acceleration that we can calculate. And stage number 2 is free fall, basically under the mercy of gravity. Okay, so stage number 1, I know the initial velocity is 0. I know the time is 5 seconds. I would like to know the velocity here because I would like to use it for stage 2. So by doing that, I can use this simple kinematic. Initial velocity 0. And I can, I have to find the acceleration first. So before I do that, so I can use F equals ma to find the acceleration. What are the forces on it? Well, I got the thrust of 20 and the weight. Those are the only 2 forces that I know of. So 20 minus mg equals ma. I'm going to solve for the acceleration. And this gives me a equals 30.2 right here. And then with that, I can use kinematics. I can use this one, or I can use something else. And with this in mind, I can find the velocity. Why do I need the velocity? Because this will help me for stage number 2. Anyway, so I can use this velocity as well to find the height. The height reached by the rocket while the motor is on. This region here. So I know the initial velocity here, V naught is 0, and then this is V final right here. Okay, so with those I can use this kinematic equation, the middle one, and I solve for y1. I have everything, and there we go. I got the height to be equal to 377.5. Now the next stage, motor stops here, and then the rest of it is free fall. Okay, there it is right here. Motor stops. See what I'm saying? And then again, whichever kinematic equation I use, I pick this one. You can pick something else. You already know, you can, well, I take it back. We don't know the time. We don't know the time here. So the other two has time, so we don't know. I think we're stuck with this one, really. Okay, so anyway, so we have that, and then we know what V naught. V naught is basically this V for stage 2. Make sense? And you just plug it in and you will find them. And therefore, the final answer now, so what is the total height reached by the rocket is y1 plus y2. So that will be equal to 377.5 plus 1163.3, and the answer would be 1540.8, or 1.5 kilometers. That's about 1 mile. That's pretty high. Okay, and there we go. Okay. Okay, I think I'm going to stop here. In the next lecture, we will be doing, there is one more topic that I need to cover, and that is the concept of friction. And then once we do that, then we will do a more advanced problem. We will do hopefully, more problem that we have done today. So wait for that, and bye-bye.